Welcome to the technical track of the Data Science Salon YouTube channel, where leading data scientists share insights and best practices of applying machine learning and AI to different industries. This video is presented by Mitchell Coplan, Senior Analytics Consultant at Northwestern Medicine. Mitchell will talk about developing and deploying a logistic regression model into the electronic health record to identify high-risk diabetic patients in an outpatient setting.
Hello, everyone. The title of this talk is Developing and Deploying a Logistic Regression Model into the Electronic Health Record in order to remotely identify high-risk diabetic patients. I'm Mitch Coplan, and I'm a Senior Analytics Consultant at Northwestern Medicine. So just to give you a quick roadmap of what we'll be covering in this talk, I'm going to go through an introduction and background. I'm going to do a problem statement. I will talk through the model development, do a little bit of talking about the model deployment, and then I'll do a quick conclusion on all of this. So some background about Northwestern Medicine, which is where I work and where we deployed the model. It's the largest healthcare provider in the Chicagoland area. It's the #1 ranked hospital in Illinois. It has over 30,000 employees, and it sees over 1 million unique patients every single year. And these numbers are all growing as the healthcare system consolidates and more hospitals are tied into the network. I think right now there's 13 hospitals and many different outpatient clinics that comprise Northwestern Medicine. So let's get into the problem. So the problem that the rest of this talk will be addressing is that there's a lot of patients with finite resources. So one of the problems we have at Northwestern Medicine is we provide care for about 60,000 diabetic patients. And of those 60,000 diabetic patients, about 1,500 of them have an avoidable hospital admission every single year. So this just means that the patients are admitted to the hospital for a reason that they really should not have been if proper care or guidance had been administered. So for example, like if they had taken their medications regularly, or if they had been regularly going to their primary care doctor, those admissions could have been avoided. And that's determined by like a quality standard. And then on the other side of things, we have a team of care coordination nurses at Northwestern Medicine. This is a team of about 15 people who help oversee high-risk patients. And they do a number of different things, but essentially they help coordinate care for very high-risk patients. So they'll do things like call up the patients to make sure they're taking their medication, or help them answer questions about their medication, or maybe see if their conditions have worsened and then schedule them for another appointment. So they do these types of things for these high-risk patients. But you can see how there's a problem here. We have 60,000 patients. We don't know who's a high-risk patient. We only have so many resources. You can kind of see where I'm going with this. So that brings us to the question, which is, which patients should be assigned to the care coordination team? The little image on the right is like, can we pick out individually which patients are high risk and who could most benefit from those services? Historically, this was not done in a very data-driven manner, and it was sort of based off gut feeling. The care coordination nurses had a number of different reports they use. So like they would look, at Northwestern, we have like a EW portal where they have access to a lot of patient data and aggregation. And they kind of use a variety of different reports to sort of see which patients they thought might be high risk based off, indicators, medical or social indicators. So we thought we could improve this method and propose creating a predictive model to identify patients that are at high risk for an avoidable admission. So this brings us to the model training and design. So we use historical data to train the model. The feature of the outcome feature that we wanted to predict was, is this patient at a high risk for an avoidable admission? we have a very robust EDW at Northwestern, and we have historical data going back all the way to like the 2000s, early 2000s. So the way we decided to design this model was we took a 2-year look back window. So we started in 1/1 of 2018 and gathered data all the way to 12/31/2019, and basically split that time in half. And at that point, we're going to say that's our prediction point. And we use the 2018 data as our future look back period, and then we use 2019 as our prediction window. So we're using data from the past year, gathering a bunch of data, and trying to say, at this time point right here, can we actually predict whether or not that patient is at a high risk for an avoidable admission within the next year? This was how we designed the study, and this is how the model data was collected. So for feature selection, we used a lot of features. Primarily, we pulled about 150 features through about 8 different areas, and you can see all these areas in the right-hand slide here. We took stuff from access, from patient demographics, from medications, from past medical history, from lab results, from social determinants of health, from utilization, like how often they're using the hospital, like going to their visits or showing up in the emergency department, and then vitals, so like blood pressure and pulse and those type of things. And then additionally, we met with subject matter experts to find additional features. So we actually talked with doctors and nurses who provide care for these patients and said, like, what do you think would be a predictive feature in this model? And we actually got some of our most predictive features just from doing that. So I think that was one big learning lesson from this project. But essentially, we had all these features. We wrote some SQL code to pull all this feature data from the EDW, the Enterprise Data Warehouse, and that's how we gathered all the data. So after we had all the data, we had to train the model. So we did this using sklearn pipelines and grid search SV, all within Python. So if you're not familiar with those different stacks, I have some code here provided on the left side. I'm very technical. I always like it when talks have code. But essentially the way this works is if you don't use pipelines in sklearn, I'd highly recommend it. But what you're able to do is do your imputation, your scaling, and your classifier all within a pipeline, so that when you go to train the model, there's easy repeatability in your experiments. And additionally, when you actually have this in production, all of those different transformations of the data are held within one place, and it's easy for somebody 5 years from now to pick that up and see exactly what's happening and be able to make changes. In terms of selecting which type of machine learning algorithm we're going to use, we were fairly diverse in what we tried to pick. We tested about 7 different modeling techniques, and you can see them all here in the code. There's logistic regression, extra trees classifier, random forest classifier, an AdaBoost classifier, a Bernoulli naive Bayes classifier, and a gradient boosting classifier, and finally a support vector machine. And we used a variety of different parameters, and the way we sort of did all this coding was by using the grid search CV package, which the grid search CV function rather. And if you're not familiar with that, I would highly recommend exploring it. But essentially what it enables you to do is you can feed in a pipeline, which is all these different ways to transform your data, and include cross-validation, a scoring metric, which we used as a ROC AUC because if you remember, we had of those 60,000 diabetic patients, only 1,500 of them actually had a avoidable admission, excuse me, and that's actually a very low percent. It's like I think less than 5% of patients. So it's very important that we actually use the ROC AUC as our scoring classifier, because we really want to limit false negatives and false positives, which is what the ROC AUC is able to do. And at that point, we trained the model and we tweaked some hyperparameters to find the best performing one. But this is some of the code we use to do that. So this next slide sort of just shows how those different machine learning algorithms performed. And you can see that logistic regression actually had the best performance. It had an AUC of 0.9, which is pretty good compared to some other modeling I've done with healthcare data, and just a quick literature review. I think that's fairly good for predicting hospital admissions. And on this slide right here on the left sort of just walks through some of the different performances of these models. So you can see logistic regression came up on top and had a mean test score of 0.89, but I were actually able to push that up to 0.9 after doing some hyperparameter tweaking. And I also would like to note that we didn't explore a bunch of other predictive models like neural networks or spent a lot of time trying to get something like gradient boosting classifier to perform better than it actually did, because clinicians are much more comfortable with logistic regression because they can directly see how the model score is being calculated by looking at the coefficients. So it's not a black box model like you sometimes see with a neural network where you kind of just throw a bunch of data at it and you're not really sure how it's getting to the prediction that it is. It just sort of, you can see what's driving those scores based off the model coefficients of those features. So we were happy with that because it makes the clinicians happy, and in general, clinicians are very not trusting of new changes to their workflow, or medicine is a very slow moving process. So like anything we can do to help sort of support that, we were happy to do. So I'm sure you're probably wondering, which features were important. So I just included, some screenshots of the top several positive correlated and negative correlated features. These are kind of maybe not the most intuitive to read, but this one stands for past medical history of heart failure, recurrent diabetic ketoacidosis. These are all features that actually we got from the subject matter experts, and they have the strongest model coefficients. So it's like I said, sometimes it's very helpful to use the people who are actually doing the work and just sort of see what their idea is for potentially good features. And a lot of these we actually got from them. This is for the negative correlated features. This is blood pressure, the value of diastolic blood pressure, and then these are just like a count of this specific type of medication, the gastroenteritis, all sorts of different random things, but when you combine them all, it actually ends up being a very predictive model. So now we have a model trained that was pretty accurate when we tested it on some testing data, and we want to actually deploy this into the electronic health record. So I'm going to leave this fairly high level because when you start getting onto the details of this, it's very technical, and I think it can kind of lose people because it's so specific to the instance that we have at Northwestern and integrating it with Epic. But I'm happy to talk more about this if people have questions about it after. But at a high level, what we did was we had that model saved as a pipeline, and we saved that as a job-lib file. And then we took that job-lib file and we created a Docker container and put the model within that container and wrote some code to pull in data from Epic and convert that into the format it's expecting it to be when we run it through the model. So once we had that Docker image or container ready to run the model, we deployed that into the Epic Cognitive Computing Platform. So this is Epic's version of the cloud. It's really just Azure in the back end, but it's Epic owns it, and it's like HIPAA compliant and integrated with the electronic health record, all of those types of things. And that's where you have to deploy the model, so it runs in the cloud. And then once it's deployed in the cloud and everything is integrated, it will actually integrate into the electronic health record. So you can see this image here is what the clinicians or the nurses and the doctors who are actually in the electronic health record might see if they click on the patient and they want to see their risk score. So you could see there's a percent likelihood of the readmission, and you can see also you can depending on how you configure this, you can include factors that are contributing to the score. So things like what's driving this 9% low risk of an unplanned readmission? Is it the number? You can see 35% of that is due to the number of past admissions, which is 4. And this is something that clinicians really like to see, because if you just give them the percent and say this is what their score is, they have a lot of questions about that, and that's not really that helpful for them. If we can say that this patient's a high risk score, and the number one reason for that is that they have a high number of active medication orders, that might be something that they can actually use in order to reduce their risk of a readmission or admission. Correlation is not causation, but we're simply providing the clinicians with more information about what might be contributing to that high risk score that the model is predicting. So we just provide the information, and the clinicians, it's up to them to use that information as they see fit. So just wanted to go through some conclusions. So this is currently running in production, and care coordination is enrolling patients into their services based in part off these model findings. This is only for diabetic patients. They have many other high-risk patients that they care for. They currently have identified over 1,000 patients to be outreached based off of the model's predictions. And we have a plan to evaluate this model effectiveness 18 months after the go live date, because if you remember, our feature prediction window, or our model prediction window, is 1 year. So we actually need a lot of data to evaluate the effectiveness of this, because it's not an instant outcome of the model. So we need at least 1 year of outcome data to evaluate the effectiveness. So we decided to evaluate it 18 months. And then I think we should also note that all this training data was used pre-COVID-19, which is really unfortunate, because I'm sure that all the healthcare patterns have changed since COVID-19. People are probably less likely to go to the hospital, and it would just change a lot of the behaviors in general. So we have a plan to sort of retrain this model, sort of in post-COVID-19 world as well. So just like to quickly acknowledge some of the people who were involved in this project. And that's it. I'd like to take any questions at this point. Thank you very much.
That was a very insightful talk by Mitchell Coplan, Senior Analytics Consultant at Northwestern Medicine. If you found this video useful, make sure to subscribe to our channel below to watch more content like this. Thank you.